Welcome back everyone to part 2 of section 4.1. So now that we have developed a geometric picture and arrived at a self-consistent equation, you could ask yourself, okay, what more is there to do? Well, the downside of this self-consistent equation, this one here, that involves the projection onto the tangent space, and it is the presence of this projection here, which depends on the solution, that makes the problem nonlinear, right? So we have, let's say, a good understanding of what is going on. But if you would actually like to solve this equation explicitly, given a particular choice of constraint manifold M, it's not at all clear what to do. And at least using this direct geometric description. And the nice thing about variational principles is that these are fairly versatile and lead to fairly explicit equations. So here the idea is that you find a functional S whose Euler-Lagrange equations are equivalent to the famous Octothorpe condition, the hashtag condition from the previous page. So let me just, in a second, flash back to this Octothorpe or hashtag condition. So one of these formulations is that the difference between the time derivative and the, let's say, the quote-unquote true time derivative as per the Schrodinger equation, this needs to be orthogonal to the tangent space of the constraint manifold at the appropriate point. So if we can reproduce, for example, this condition here using a functional, then we're golden. And indeed, this is what we will, of course, now do. So let's start with some requirements that help us understand what the shape of this functional should be, what kind of functional it should be. So quite immediately, we have two requirements. So the first one is that S should map potential solutions or potential approximate solutions to real numbers. And what is the form of these solutions? Well, they are time-dependent paths on M. And the second point is also relatively clear, namely potential solutions should, of course, satisfy the initial conditions. So now let's propose a particular functional and then check whether it does the job. So that's the approach we will take here. So I propose the following functional. S should map a path phi epsilon. So phi epsilon here is an entire path. It's not just a point on M, but a path on M, which depends on time. And because our problem is time independent, I can choose the initial and final time arbitrarily, and so I choose the initial time to be 0. That's just a matter of convenience. And then I'm integrating the scalar product of phi epsilon of S with I epsilon ds minus h epsilon applied to phi epsilon of S. So, of course, I'm going to make some implicit assumptions here. So one assumption is that M is not just a subset of the Hilbert space, but a subset of the domain of the self-adjoint operator H epsilon. And that is important because then I can, to show that this here is real valued, so this here is real valued, as we shall confirm now. So if phi epsilon of S lies in the domain, then because H epsilon is self-adjoint, we can push it to the other side. And also this factor here so the time derivative can be pushed to the other side by partial integration. Okay, that gives us a minus sign, but we also have the purely imaginary prefactor I epsilon here. So once we push that from the right to the left argument of the scalar product, we incur another sign change, and these two sign changes cancel. And that means that this expression here equals its complex conjugate, which means it's a real number. Of course, the definition is not yet complete because this is a functional. We have to endow it with a domain. And the domain here not only depends on the initial condition, but we also have to choose, if you want, a final condition. So we have to constrain the starting and the end point of the path. So if you've seen variational principles in classical mechanics, this is exactly the same thing. Also there you had to choose initial and final points, even though you did not know whether the trajectory will actually join up initial and final point. And you will have to do the same here. For our purposes, only the initial condition has physical significance. And okay, what is the domain? Well, these are just paths, which are C1, from the relevant time interval, which is 0 to t, to m. And then we have to constrain the initial point. So at time 0, the particle must be in state phi naught. And at the final time, which is t, the particle or the solution shall be in equal to phi 1. But again, this guy here is arbitrary. Okay, so now we have to look at the stationarity condition. So we have to take the first derivative of this functional and set it to 0. But of course, here, because we're working with functionals, it's actually not so easy to actually define, or it's not immediately obvious what the stationarity condition actually means, right? So what's the mathematical definition? Of course, if you've seen this before, if you've taken a course that covered classical mechanics on manifolds, for example, then of course you will know this. But I'm just trying to proceed under the assumption that perhaps you do not. So the first thing is that this condition here, let me color this maybe. That this condition is actually, if you write it out, as follows. It means that ds phi epsilon applied to a tangent vector phi epsilon is equal to 0 for all tangent vectors phi epsilon. But tangent vector in what sense? Well, it needs to be an element of the tangent space at phi epsilon of our domain. Okay, that's maybe not a big improvement. So let me actually define what I mean by this, and then give you another characterization that makes it a little bit easier to work with. So the tangent space, of course, phi epsilon is a trajectory that starts at phi naught and ends at phi 1. So it's not a point on the constraint manifold, but it's a particular path on the constraint manifold with fixed initial and end points. So this is defined as, well, as you know, that there are several ways to define tangent vectors, and And I'm going to choose the one that talks about equivalence classes of paths. So here I'm taking, and this is what I call phi epsilon. This is equal to the derivative in deformation parameter mu of gamma epsilon mu at mu is equal to 0. So I will draw a picture in just a second. So what is gamma epsilon mu? So, well, there exists delta and a C1 map. And this C1 map has a parameter mu, which comes from the open interval minus delta to plus delta. The size of the interval, as long as delta is strictly greater than 0, doesn't really matter. So this is a path in d phi naught phi 1. So you can think of this as a homotopy of paths. So, but it's a little bit confusing perhaps because you have time as a parameter and you have this mu as a parameter. And this gamma epsilon mu shall have two, has to satisfy the following condition. If I evaluate, if I set mu equals to 0, well, then I get phi epsilon. So this is what it means for this to be a tangent vector. Of course, it's not a one-to-one correspondence between these vectors and gamma epsilon mu's. There are many paths that lead to the same phi epsilon, so the actual tangent vectors should be thought of equivalence classes of such gamma epsilon mu's. In our case, and this is the important point, is that there is a relation between this tangent space and the tangent spaces at the of the manifold itself. So this is a small claim. You can think of it as a little lemma, and that is that you can identify T phi epsilon d phi naught phi 1. So that's the tangent space at phi naught to the domain of our functional. We can identify this with paths in time that take values in T phi epsilon of S at M. So this is the tangent space to the manifold at the point phi epsilon of S. And since this point will change in general with S as you vary S, these at different values for S, the right-hand side should be thought of as distinct spaces. And of course, there is an additional condition, and that is that at the initial time 0 and the final time t, the tangent vectors must be 0. And that is because you fix the initial and the endpoint. So let's just confirm this small claim. And this is more, let's say, to help you work with these definitions. So we pick some phi epsilon from the domain. So they're actually, if you want, they're what we will actually have to prove is two inclusions. We will have to prove this inclusion, and then we will have to prove the converse inclusion. But the converse inclusion is just obtained by reading this inclusion backwards, if you want. So we first pick a point, which is the base point for the tangent space. And then we pick a tangent vector at the tangent space. And that means that by definition, there exists a path gamma epsilon mu. So this is a path in mu. With the following properties. Well, first of all, if we evaluate gamma epsilon mu at mu equals to 0, we get phi epsilon back. So that's this bit. And then the other one is that the derivative in mu of gamma epsilon mu evaluated at mu equals to 0 is our tangent vector phi epsilon. Okay, now we have to distinguish points in the interior of the interval 0t, which are not kept fixed, and points at the points s equals to 0 and s equals to t. So first we fix s from the interior of the interval 0 and t. So s equals to 0 and s equals to t are excluded by assumption. And then we just evaluate what we've written here at the time s, right? So then the above two equations tell us that gamma epsilon mu evaluated at s, and after setting mu equals to 0, this is just phi epsilon of s. And the tangent vector is evaluated at s, gives me d mu gamma epsilon mu of s, and then I set mu equals to 0. But now I just make the stupid observation that if you fix s and regard this as a function of mu, then this is a path on M. So for fixed s, and if you now view mu as the relevant parameter, this is a path in M. And so this here is actually, so okay, sorry, so this here is a So S fixed seen as a function of mu. This is a path on M. And that means that this here must be an element of the tangent space. Okay, what is our location? Well, it's phi epsilon of S to M, right? And this was this claim here. And now for the special points, S equals to 0 and S equals to t, we can apply the exact same argument. So let's just do it for t. So here, because the gamma epsilon mu is in d phi 0 phi 1 for all mu, this means that if we evaluate gamma at 0, let's say, this is always equal to phi naught for all mu. And so this is the constant function. In mu. And the derivative of the constant function is 0. And of course, this also this holds for all mu, but in particular, it also holds when I restrict to mu equals to 0. And the same argument holds for S equals to t, obviously. And the only thing that we now need to clarify is the other inclusion. But let me just say the other inclusion. So you start with such a function here, whose initial and endpoints are fixed to 0. Then there exists a path gamma epsilon mu, so that you have this identification also in the other direction. But okay, to do this, you just need to read the above arguments in reverse. So what's the upshot here? The upshot is that if you take a tangent vector on the domain of the functional, then this is a path in the tangent spaces of the approximation manifold in this precise sense here. And with that, we can actually then compute the derivative. So now let's compute the stationarity condition. The stationarity condition ds at phi epsilon is equal to 0 means that ds phi epsilon applied to all tangent vectors, phi epsilon is equal to 0. But here it's a tangent vector to the domain of the functional. So this is the slight curveball. And now we just need to compute it, right? So we pick phi epsilon. Then by definition there exists a path gamma epsilon mu, so that gamma epsilon mu evaluated at mu equals to 0 is phi epsilon, and the derivative in the deformation parameter mu evaluated at mu equals to 0 just reproduces our tangent vector. Okay, so now the definition of the derivative in the direction phi epsilon is, well, it's d mu of s, and now as argument we take the homotopy gamma epsilon mu, and then we evaluate at mu equals to 0. And now if we place the if we do the dot the i's and cross the t's, we can see that in the conditions that we're interested in, the derivative and the integral in S commute. So it's the integral from 0 to t ds, and now we have the derivative in mu of the scalar product. And now in both arguments you have gamma epsilon mu evaluated at s, and then in the other argument you have I epsilon ds minus h epsilon applied to gamma epsilon mu of s. Now you can use the continuity of the scalar product in both arguments. You have to, of course, impose some conditions on the domain of the operator so that the derivative with respect to mu commutes with this operator here. Basically, you have to make sure that the derivative, that the tangent vector phi epsilon also lies in the domain of the operator. But I will, let's say, these are just some technical conditions. If you believe that they are satisfied, at least once I impose more explicit mathematical conditions on the operators involved, well, then I can actually do the computation. So I get two terms. So first, I get phi epsilon of s, which comes from taking the derivative of the first argument. And then I just have to copy the second argument, I epsilon ds minus h epsilon applied to, and of course I evaluate the whole shebang at mu equals to 0. And if I do this for the right argument, I'm just getting phi epsilon of s. And for the second term, well, this guy and this guy, they just trade places. So here I have the non-tangent phi epsilon on the left, and I have the tangent phi epsilon on the right. But now if you remember the arguments that I made to show that the functional itself is real valued, the same arguments apply, which show that this guy here, well, that I can push this here to the other argument, and then this is just equal to the tangent vector phi epsilon of s, taking the scalar product with minus I epsilon ds minus h epsilon applied to the base point phi epsilon. But of course, now I have to add the complex conjugate here. Okay, so we can simplify this by just noticing that this is twice the real part of either one of the two. And for reasons that are not completely clear at this point, it is convenient to factor out an epsilon or an I epsilon in a sense. So I'm getting rid of this here. And instead I have a 1 over I epsilon as a prefactor of the Hamiltonian. I have an imaginary part here. And then, well, I get a factor of minus 2 epsilon in front. And this has to be 0 for all tangent vectors phi epsilon. Oh, sorry. So this has to be tangent to the domain at phi epsilon. Okay, so I can just copy and paste this condition here and proceed on the next page. So when is this condition satisfied? Well, the thing is, the imaginary part does not really play a role for the following simple reason, because of this identification again with functions in time that take values in the tangent spaces to the approximation manifold. This here is a complex vector space. So what I can do is if phi epsilon of s is in this tangent space, then I can also multiply it with the imaginary unit I, and it is again in the same space here. And I can use that because what I can do is I can just add let's say a factor I here. But if I factor it out, then okay, if this is true with and without the imaginary unit I, then this means that the real and the imaginary part of the scalar product have to be 0, which means that just the scalar product has to be 0. And this here is nothing but the hashtag condition from before. And this shows that the condition, that the functional reproduces accurately the orthogonality condition. The stationarity of the functional is equivalent to the orthogonality condition from before. So now you might ask, okay, so this was a lot of work. What have we gained? Apart from computability and some error estimates and so forth, there's one thing that I would like to mention at least, but not really get into more depth in. But I think that if you're really working with this is something that's absolutely crucial because you really rely on it. Not least by calling a semiclassical approximation an approximation by Hamiltonian equations. And that is that this problem has a symplectic structure. So if you look at the Bible of classical mechanics, Marsden and Ratio, specifically chapters 2.2, 2.5, and 5.3. Then you will see that they explain how to recast the Schrodinger equation in the form of a Hamiltonian equation. Of course, these are linear Hamiltonian equations. Okay, and just to give you an idea, the symplectic form should feel familiar if you've just had a look at the previous page. It's nothing but minus 2 epsilon, the imaginary part of the scalar product. Right? So it's exactly this combined with this here. And this is important, right? Because if you believe for a second that this is this map satisfies the axioms of a symplectic form, you also see that this functional is compatible with the symplectic structure, and that leads to an inheritance of the symplectic structure to the dynamical equation on the defined with respect to the constraint manifold. So the symplectic structure of the Schrodinger equation this induces a symplectic structure on M. So I'm being very vague here. So there is actually a step in the middle, because it is more immediate that the symplectic structure of the Schrodinger equation induces a Poisson structure of functions on M. And in case of semi-classical approximation manifolds, this leads to a symplectic structure. But it's not completely... it's not true that every system with a Poisson structure also has a symplectic structure. But the other direction is correct. So if you have a symplectic structure, then this induces a Poisson structure. Just to give you another idea how this translates. Okay, and this here is known as symplectic reduction. So this, there are standard tools, and this is the important point. This is a symplectic reduction. So that means that the symplectic structure can be computed from just the symplectic structure of the Schrodinger equation and properties of M. That is extremely important. Just to give you an idea, a feel for the symplectic structure of the Schrodinger equation, we know that the solution to the Schrodinger equation, which is the unitary evolution group, unitaries preserve the scalar product, so they preserve also the imaginary part, and they also preserve the imaginary part multiplied with some arbitrary constant. So that means that the unitary evolution group can be interpreted as a symplectic map. So hopefully this gives you just a feel for why this approach can be quite powerful, because it taps into a lot of themes that are common in variational approaches to classical mechanics. And also, I hope I've given you at least a feel for how to actually formulate the different conditions that characterize the elements of a best approximation, the best approximation of the true solution to the Schrodinger equation by a solution that is constrained to M, to the approximation manifold. All right, that's it for part 2.